All right, now, again, Newton's laws. A lot of this is revision from year 10. So we went through the first law, we went through the second law. You should be able to give me the definition of the first law. Remember, the important thing is you have to recall it, recite it verbatim. Every single word needs to be present in order for you to get the mark for that definition, okay? Because every word is significant. You take one word out and then the whole definition changes completely, okay? For this one, for every action force there must exist, and I've just realised I've misspelt exist. Exist an equal and opposite reaction force. Now, this is a very easy equation. It's F action equal and opposite F reaction. Okay? Now, here's the important thing. You have two forces and they each have to act on two separate objects. So, Bergsma and Thomas, can you please close your laptop?
I was here, so I'm just doing stuff that I missed last week.
Okay.
That's not it.
I'll just have to take your word for it. Justin, do we need our laptop open?
It's right.
Translator?
It's
Okay.
right.
No worries. So, here is the thing. You need two objects. One force acts on object 1. The other force acts on object 2. It's a bit tricky because sometimes we don't see the other object or the other force. And I'll go through a few examples. The easiest example would be the recoil of a gun. Try and draw my gun as best I can. There's a gun. This looks like a pistol, but anyway. Here is mass 1, and then we're going to spit out mass 2. Now, the problem is when we draw our forces, we generally draw them as free body diagrams. But just below, I'm going to draw F action, and that's going to act on M2, and then F reaction is going to act on M1. Okay? Now, you've got the two masses, equal and opposite. So you might notice I have drawn my vectors opposite direction and equal magnitudes. Okay, so these are the little tricky things that they can try and trip you up. That a lot of people see that the bullet is ejected with a much faster forward velocity than the rifle recoils backwards. So some people might think that there is a greater force acting on the bullet because it's seen to be travelling faster. But no, the second law would say that, hang on, your force is acting on a much smaller mass, and so it's going to accelerate by a much greater amount, and that's why it leaves with a much faster speed. Okay? All things being equal, two equal masses, they would travel off with the same speeds. Okay? So, they are always present. And this is why it's a law, because they have not found in science or nature an example where you get one force acting. There are always two. So I'll just highlight that one acts on one mass, the other force acts on the other mass. You need two. So with gravity, well, let's just use the collision here. That one's pretty easy to see. Collisions are a pretty good example. So let's just say a cart travels in. Let's call this U1, M1, and it's travelling with a speed, so that's why it's got the speed lines. And then it collides with a stationary mass, M2. Have a think. If they're equal masses, we'll actually be able to replicate this later on in the term. If they're equal masses, then that mass 1 should stop. Mass 2 should then travel off with exactly the same speed. All of the momentum's been transferred. But again, let's just quickly draw our FA and FR. It's exactly the same. But what happens is a very interesting equation comes out, which we will look at towards the end of this booklet. And it comes from Newton's third law. And second and first. All of them are involved. So let's just have a look. M2, A2 equals negative M1 A1. I've just thrown in Newton's second law. We know that F equals MA. And if this is the unbalanced force, then we would get an acceleration. So what's going to happen is M2 is going to accelerate that way, maybe a positive direction. M1 is slowing down. It's going to decelerate. It's going to accelerate that way. It's slowing down. That's why there's the negative there. Okay? If the negative wasn't there, that would break the laws of physics. That would be it colliding and they suddenly travel off faster. You're not conserving momentum and you're not conserving energy. But then Isaac Newton went a step further and said, well, hang on, let's throw in V take U over T. V take U over T. Now, this should be easy to understand that cart 1 is in contact with cart 2 for the same time that cart 2 is in contact with cart 1. So we can cancel out the times. All right? And then this gives M2 V2 take M2 U2 equals negative M1 V1 plus M1 U1. Now, if I put all the U's on one side and all the V's on the other, we get M1 U1 plus M2 U2 equals M1 V1 plus M2 V2. This is the sum of momentum initial equals the sum of momentum final. This is called conservation of momentum, which we are going to learn later.
In a test, can you use brackets for the M2 V2 minus M2 U2 or not?
You can,
To make it
but really,
timing two things.
we've got to be careful. When we do this topic, we need to be careful because it depends on the direction. If U2 is in the opposite direction, it'll have a negative, and there'll be double negatives occurring. Don't worry about anything beneath that line. We're going to cover this equation down here, I think, in about week 7 or week 8. Okay? But again, it is a consequence of Newton's third law. Okay? So as cart 1 applies a forward force to accelerate cart 1, then cart 2 is pushing back equal and opposite, which decelerates. Now, weight and normal is tricky. And I'm going to show you why that is. So, here we have a person standing on a surface. Nice, flat, horizontal surface. We know that there is a gravity force pushing him down. Force of gravity is mg. And then we have another force, the normal force that's pushing up. Now, let's just put some values in. Let's say that he's 60 kg, in which case we can work out the gravity force. That's 60 by negative 9.8 is 588 newtons downwards. Now, if a person is standing at rest, we need to recall Newton's first law, that all the forces acting upon him are balanced. So I'm just going to remove the normal force for now and say if that was the only force acting on him, then he would be observed to be accelerating downwards at a rate of 9.8 meters per second. He would be in free fall. But he's not. He is at rest. So we know that there has to be some force equal and opposite that acts upwards. And that's the normal force. Now we'll just go F subscript N, capital N for normal force. Now the normal force is a reaction force. Okay, so if you're pushing down, then the floor pushes back up. Okay, and we know sum of all forces equals 0. Now I'm going to write in what those forces are. And this is where you need to show your mathematical logic. Every one of you should be able to tell me that the normal force has to be 588 newtons upwards. but you've got to show it using some mathematics. You've got to show it using your logic. Now I'm going to assign that gravity is negative. Acting downwards is negative, acting upwards is positive. So if I wanted to rearrange, I could go Fn equals negative Fg equals negative It's a lot of work, but you don't want to risk losing marks. All right, if you just go Fn equals 588 upwards, you're only really doing 1 mark for what might be a 3-mark question. Okay? So again, in all of these vectors, assign a convention. If you just write down is negative, up is positive, then that's perfect, because then you can start assigning pluses and minuses when you're combining your vectors. Okay? Now, just a few things. I want you to write a couple of things because it's pretty easy, but I don't want you to lose any marks. We've got W is weight, W equals weight, but I'm going to write it as F lowercase g, the force due to gravity, and that's obviously measured in newtons. Your mass has to be in kilograms, and g is your gravity, your local gravity, which is in meters per second squared. Okay? Now, we say local gravity because we could be cruel and put you on the moon where the local gravity is 1.6. If you're not told anything, assume you are on Earth. So a book on a table, calculate its weight. I don't want you to go, oh, where is the table? It's on Earth, all right? Unless you might be given a question where, a table on Mars, you would need to know what that gravity value is. So if you're not told, assume that it's 9.80. Okay? Now the thing about weight is it's always acting. It's always acting, and it's always downwards. All right? So from the minute you are born to the moment you are put in the ground, there is a force due to gravity pushing your mass towards the centre of the Earth's mass. Now, you can't really move around the Earth such that the centre of the Earth is not directly beneath you. So I'm pretty confident if I hold a plumb bob on a string, that string is going to be pointing towards the centre of this big sphere that we're stuck on. Okay, so it's always down. Right? We don't have to draw the surface as a sphere. We know that we're on a sphere or a disc. I've seen the YouTube videos. Now, here's the next problem. These are actually 2 different forces from 2 different action-reaction pairs. I just want to now draw our current understanding of the Earth. Let's just, for the sake of example, say that we're up at the top. Now, here's my force of gravity, right? That's the force of the Earth pulling you down. You are actually pulling the Earth upwards with equal and opposite. So, okay, if I have a weight of 700 newtons, I'm actually pulling the Earth towards me with a force of 700 newtons. But if I fall off the table and I accelerate downwards, it's because my mass is so light, my acceleration is quite significant, it's 9.8. But actually, if I was to fall off the table and accelerate towards the ground, during that acceleration, I'm actually pulling the Earth towards me. The Earth is actually accelerating towards me. But its acceleration is going to be 700, over about 6 times 10 to the 24. That's the mass of the Earth. So you divide 700 by 10 to the 24, its acceleration is going to be 10 to the negative 20 something. It's not going to be measurable. So really, I need you to appreciate that this force is the reaction force to me pulling the Earth towards me. Now let's go, what about the normal force? Well, I'm actually pushing the Earth down. I'm applying a force to the floor of the Earth, and then the Earth says, nah, I'm not going to let you do that. I'm going to oppose that. So there are actually 4 forces at play. 2 are acting on the Earth. We don't care about them. And then 2 are acting on us. Does that make sense? Cool. So the downwards red arrow of gravity and the upwards reaction force, or the normal force of the surface. Okay? Now, on a deep philosophical level, the reason why I don't fall through the floor is because there are electrons involved in bonds in the surface of the floor, and there are electrons involved. This is my shoe. There are electrons involved in the surface of my shoe, and there's a special rule that says that electrons can't exist in the same space with the same spin. It's called the Pauli exclusion principle. And as you get those electrons closer to each other, there's going to be an electrical repulsion. Remember, 2 charges, if you bring 2 like charges together, they repel. So really, you can never truly touch something, because you can work out the physics that the electrons are going to be at a certain height above the surface of each surface to produce a repulsion that provides the required normal force. So don't worry about that, but it's an interesting thing to think about, that you can never truly touch something because the electrons on your fingers can never be in the same position as the electrons on the table. Okay, over the page. Here is another example of an action-reaction force, friction. It will oppose motion. For example, a ball rolling along that way, okay, we can draw in the gravity force, the normal force. In the vertical, Spencer Bergsma, they are balanced in the vertical, and so the ball would not be observed to be accelerating down or up. But if the ball is moving to the right, then there would be a backwards force. Okay? That would eventually slow it down. So now, if we look at this example, this is no longer in equilibrium. The sum of all forces does not equal 0. There is a backwards force, and F equals ma, the acceleration will be backwards. So this is an example of an object travelling to the right, accelerating left because there's an unbalanced left force, and that causes its acceleration to slow down. The crazy thing is, once V equals 0, friction removed. Imagine you've got this backwards arrow while there's motion, and as soon as the object stops, that force disappears. Have a think. If that didn't disappear, the object would slow down, stop, change directions, and start speeding up. That doesn't really happen. If you throw a bocce ball or a tennis ball along the grass, it rolls to a stop. It doesn't roll back and accelerate back towards you. Okay? Whereas gravity, remember gravity, if I throw something up, gravity is always acting always downwards. So yes, I throw a ball up, it comes to a stop, changes direction, and then accelerates back down. But with friction, you got to imagine that that kind of turns off once there's no motion. Okay? Or we can have so this is an example of sum of all forces not equaling 0. Or you can have it in applied force. So here, weight of the fridge, the normal force of the surface pushing back. If I now apply a force here, providing I'm not overcoming the limit of friction, there would be a backwards force of friction. And then we could say that maybe this guy is in equilibrium, that the vertical forces are balanced. The fridge is not accelerating up into the sky or down through the floor. And in horizontal components, they're also balanced. So the fridge is not accelerating left or right. So this could be an example of equilibrium. If you, just by the way, I think if you were asked for a free body diagram, hang on, let me just, I have an exercise later in the booklet. You draw the object as a square and you draw the forces originating from the center, like so. Okay? If it's in equilibrium, your teacher is looking for all of these forces to be equal in length and opposite in direction. So we could draw here Fn, Fg, Ff, and Fa, applied force. Okay? Now, again, the reason that friction exists is because if we zoom in on the surface, there are tiny microscopic irregularities. There are going to be little nooks and crannies and crevices and valleys and hills, and they sink down into each other. And so you can imagine if you tried to move one lateral to the other, if you tried to move one sidewards, there's going to be regions. Now let me just redraw this orange. There's going to be regions where they come into contact. So if I try and push that way, then there's going to be equal and opposite reaction forces. It's a bit hard to draw. But we're only action and reaction. So I've just drawn sort of three instances there where the surfaces, again, you think of a table and a book, you go, oh, they're perfectly flat. So there shouldn't be any region where they're meeting vertical contact. But if you zoom in, you would see that the book is not a flat surface and neither is the table. Okay? We can try and remove that by polishing the surfaces. So you can get out your cut and polish and buff it down. You can lubricate the surfaces. You can fill the gaps with a fluid, with oil, so that it slides across the top. Oil being incompressible, it basically sort of floats atop it. So there are ways to minimize friction. There are ways to increase friction. It comes down to whether you want these cracks and crevices or whether you don't want them. Okay? Now, we actually look at... Yes? Okay, go. Jam on. Please watch this section of the video because we are doing an investigation towards the end of the term that is going to involve this equation. Okay, so it is quite important. There is a limit to how much friction an object can oppose. I'm going to use an example of this pile of books. Oh, people nearly dropped. Alright, now, pile of books. Weight down, normal up, equilibrium. If I apply a force, you're just going to have to believe me that I'm actually pushing on this object, but it's not moving. So if I'm applying a 1 Newton force that way, friction is applying a 1 Newton force that way. Let me double it. Let me double it. Now I'm applying 2 Newtons. Friction is applying 2 Newtons. Now let me go to 3. Are you ready? So I apply 3 Newtons. Oh look, it's starting to accelerate. So I know that the friction force must be less than 3 because I applied a greater value than what it could oppose. So there is a maximum. There's a maximum force of friction. And if I need to apply a force greater than that, then I can accelerate it. So the equation is really easy. Here we go. The force of friction equals mu s times n, or let's go Fn. It's a coefficient. This is called...
Is that S a variable or a subscript?
So it's mu subscript s times the normal force. Now, this mu is called the coefficient of static friction. It depends only on the two surfaces that are in contact. So have a think. The normal force is always going to be equal and opposite to the weight force on a level surface. So that's not changing. What we could change is what the surfaces are made of. And so there are some surfaces, it's a pair. You need both surfaces to produce this coefficient. For example, a really good grippy surface, such as concrete on rubber, might have a coefficient that's quite high at around about 0.9. Meanwhile, something that might be a little bit slipperier, ice on ice, might have a low coefficient of 0.1. And then there's There's heaps of tables in engineering books on different surfaces. What type of wood? Has it been sanded down to a certain polish or extent? Metal on wood might be around 0.4, for example. No, it's just, so here's the thing. It's dimensionless, because have a look. Your normal force is measured in newtons, and your friction force is measured in newtons. So if we did a bit of rearranging, if I did force of friction divided by the normal force, it's dimensionless. Okay? Now, could I get you please to plot friction force as a function of the applied force? So we're going to replicate my demonstration over there about me pushing on the object. So let's start with 0, and I applied 1 Newton, and the book was able to oppose 1 Newton. So I said, you know what, let's go to 2 Newtons. And wouldn't you know it, the book was also able to oppose 2 Newtons. And then I opposed 3. Then what happened is it got to some point, some limit, some maximum value of friction beyond which it could not oppose the applied force. And what happens is it actually drops down a little bit, and then it just travels off. Now, this bit here, this is called FF kinetic, and this bit here was FF static. Now it's interesting, and again, it'll be some certain value. We could do an experiment. It won't be very interesting, or it'll be pretty boring. Hugo, we attach a force meter to our box, and we just increase the force. It'll get up to a maximum, say 2.5, and then as it starts sliding, you'll notice that it drops slightly. So have a think back to when an object is stationary, all of the cracks and crevices are sitting in each other. Once it starts moving, they rise up, and now they're kind of just drifting over each other. They don't really have the time to sink back down. That's the best example to explain why the static friction might be 2.5, but once I get that box sliding, the kinetic friction while it's moving might drop down to 2. Okay? Yes?
Does the gradient of the kinetic, FF kinetic, just like keep going to like get close to 0, or does it just decrease?
Well, so this, if we said FF, that's rise over run. Well,
but for the kinetic bit, like for the FF kinetic, does that just keep like getting close to 0?
No, it stays constant.
Okay.
It'll stay constant. So once if that's maxed out at 2, and I apply 5, then we've got an unbalanced force of 3 forwards. It'll just accelerate at a greater rate. Okay? So let's just go over to an example. Okay? And I'll get you guys working for a bit too. So, a 50 kilo mass sits on a surface, and we've got a coefficient there. Okay. A force of 800 newtons is applied. So let's draw some stuff in. Here is our force of gravity. Here is our normal force. Let's apply a force of 800 that way. Okay. And then obviously we need to figure out what this guy is, FF. Okay. Now I'm going to assign a convention that the applied force is acting in a positive direction, friction is acting in a negative direction. And let's just put in our 50 kg. Now, our force of friction equals mu s times normal force. So here's the thing. We need to do a little bit of a side mission and go, well, I know the sum of all forces in the y equals 0, which is gravity plus Fn. Therefore, Fn equals negative mg, equal and opposite. So if I've got 490 newtons downwards, then my normal force must be 490 newtons upwards. Okay? So that was the little side mission there. You know, if you just wrote mg, it's not quite right. And I'll give you an example in just a moment as to why it's not the weight of the object, it's the normal force of the surface. So now we can go back up to our friction force and say, well, basically, the maximum friction is going to be 60% of that. That's what your coefficient is saying. Times this number by 0.6, that's the maximum that it can provide. So let's go 0.6 by 490 equals 294 newtons. So now I can say, well, now we've got an unbalance. So you could look at this and go, well, if I apply 800 newtons forwards and the backwards force is only 294, you can figure out the net force. So the sum of all forces in X is going to be applied force plus force of friction. And then we can bring in Newton's second law that this unbalanced force will produce an acceleration okay. I'll just scribble out that for a second, because that's beyond what we've learnt so far. So this is something that you could be expected to do. Now, obviously, we've done probably 3 separate questions there. So I could throw this in. Question 1, 12 marks. Part A, determine the normal force and the weight force. Part B, determine the frictional force. Part C, determine the unbalanced force. Part D, determine the acceleration. And each time it's 3 marks, 3 marks, 3 marks, and 3 marks. There's 12 marks there. And you've got 12 minutes to do all of that. Okay? Or in the exam, section 1, it could just be you've got 1 page, 8 marks, determine the acceleration. So, you could get this in section 1 of the exam. Section 2 is generally longer questions that are in parts A, B, C, and D. Now, the reason why, again, I don't know if you have this misconception, but I don't want anyone to have it. The reason why it's the normal force and not the weight force is because you could be pushing down on the object as well as gravity. So, Jamon, get up here. We're going to do a demonstration. You're going to use your imaginations. Okay, let's say we've got 20 newtons on papers here. So right now, 20 newtons down, 20 newtons up. Let's say coefficient is 0.6, so I know that friction is 12 newtons. Right? Now, Jamon, push down with 20 newtons. Okay. Now what Jamon has just done has added an extra applied force. So use your head now. You've got 20 newtons of weight, 20 newtons of Jamon. What does the normal force need to be? 40. Great. So the normal force is 40. Now what I'll notice, if I now try to apply the same force, I'm not going to get it moving. So the harder you push down on the surface, the normal force increases, and the required frictional force would also increase. So now it would be 0.6 times 40. It's not 12 newtons, it's 24. Thank you, Jamon. So just remember that. It would be a nasty scenario. You'd have all of these force vectors. I could be pushing down at an angle, but if I push down now, I mean, here's, okay, perfect example. This could go pear-shaped, but all right. The weight force is acting down. The normal force is acting out, and friction is now acting up. So obviously, I'm not going to let go of this, how am I going to explain what the hell I'm doing here? I'm pushing it into the wall. I'm pushing it into the wall. The wall's pushing out. Friction, okay, let's say it's 20 newtons of weight. If it's 20 newtons of weight, what does friction have to be equal to or greater than for this not to slide? 20 newtons. So 20 newtons up. I need to be pushing in with enough force so that the normal force is great enough so that when you multiply it by the coefficient, it's greater than 20. If I let go, it's going to start sliding. So I'll give you this tricky question. Do we have some spare paper anywhere? Yeah, let's go to the bottom here. Ignore that crap, that's too easy. Let's do an example. Mr. Murray holds... That's my hand. Two kilos, okay? M equals 2 kilos. Coefficient is 0.7. Okay. Then, okay. Have a chat amongst yourselves. This is a strange scenario that, again, since the object is in equilibrium, the applied force and the normal force must be equal and opposite. And since it's not going up or down vertically, then the weight force and friction force must be equal and opposite. So you've got to figure out what do you need to determine first in order to determine the next force, in order to determine the next force. Have a chat with your colleagues, figure out with what force must I push the book against the wall so that it doesn't slide. Please and thank you.